Good evening, Miss Anis. Today, our group will be presenting the application of conic section in real life. First of all, I will introduce my group members who are me, Vera Samueleng, Crystal Yap Wenjing, Nicole Lee, and Damia Zulaika. In our presentation, we will focus on the parabola. I will give an introduction of conic sections. The conic section is also called conic. In geometry, it is any curve produced by the intersection of a plane and a right circular cone. Depending on the plane's angle relative to the cone, the intersection is a circle, an ellipse, a hyperbola, or a parabola. Based on the analytic definition, a conic may also be described as plane curves that are the paths or loci of a point moving. Thus, the ratio of the distance from a fixed point, which is the focus, to the distance from a fixed line, which is the directrix, is a constant. This ratio of distance is called the eccentricity of the curve. We can know the shape of conic section based on the eccentricity. If the eccentricity is equal to 0, it is a circle. If equal to 1, then it is a parabola. If it is more than 0 but less than 1, that means it is an ellipse. If more than 1, it is a hyperbola. Now, let us talk a little bit about the Greek origins of the conic section. The early history of conic sections is joined to the problem of doubling the cube. According to Eratosthenes of Cyrene, the people of Delos consulted the oracle of Apollo for aid in ending a plague and were instructed to build Apollo a new altar of twice the old altar's volume and with the same cubic shape. If you do know altar is what? Altar is the things shown in the picture. Perplexedly, Delians consulted Plato, who stated that the oracle means not that the god wanted an altar of double the size, but that he wished, in setting them the task, to shame the Greeks for their neglect of mathematics and their contempt for geometry. Hippocrates of Chios was the first one who discovered that the Delian problem could be reduced by finding two mean proportional between alpha and 2 alpha, which represent the volumes of the altars respectively. Later, Archimedes showed how to use the conic sections to divide a sphere into two segments having a given ratio.
So next, I'll talk about the importance of conic section in mathematics. Conic section is very important because they are used in many real-world applications. Firstly, conic section plays an important role in astronomy. This is because the orbits of two massive objects that interact according to Newton's law of universal gravitation are conic sections. For example, when the objects are moving apart, then both objects follow parabolas or hyperbola shapes, while when the objects are bound together, then both will trace out ellipses. In addition, conic sections are always smooth more precisely and they contain no inflection point. So there's a picture in the middle shows the inflection point. An inflection point is the location where a curve changes from sloping up or down to sloping down or up. A smooth surface is required to ensure laminar flow and prevent turbulence. Therefore, we can note that conic sections are also very important in aerodynamic applications. For example, the aircraft, wind turbines, propeller, ground and marine vehicles. Last but not least, conic sections have an aesthetic appeal and are often used in art and design. It helps to create visually delightful and balanced compositions also. For instance, both the Eiffel Tower in Paris, France, and the river bridge in Godavari at Andhra Pradesh, India, their design involved the conic sections also. Next, our group will show about the problem statement and the solutions. So I'll pass it to my group member Damia.
Okay, here I'm going to proceed for problem statement and the solution. The first question, Given a bridge has a parabolic arc with 10 meter high in the center and 30 meter wide at the bottom, choose the vertex as the origin and the axis of the parabola as the y-axis. The parabola is open downward. Find the height of the arc 6 meter from the center on either side. First thing to do is we're gonna draw the diagram based on the question given, and the diagram is shown below the question. By our choice of equation of parabola is x squared equals to negative 4ay. Coordinate b, 15, negative 10 is point on the parabola. So we're gonna substitute it into the equation and we get 15 squared equals to negative 4a multiplied by negative 10. 4a equals to 15 squared over 10. The equation of parabola becomes x squared equals to negative 15 squared over 10 multiplied by negative y. So this equation gonna be our second equation. D is a point 6 meter from the center. DE is the height of the parabolic arc at a distance of 6 meter from the center. So let the coordinate of E be 6 negative y, and substitute into the equation 2. We get 6 squared equals to negative 15 squared over 10 multiplied by negative y, and answer is 1.6. Require height DE equals to CF equals to CO minus OF. DE equals to 10 minus 1.6, and we get 8.4. Okay, for the second question, an engineer designed a satellite dish with a parabolic cross-section. The dish is 5 meter wide at the opening, and the focus is placed 1.2 meter from the vertex. A. Position a coordinate system with the origin at the vertex and y-axis on the parabola axis of symmetry, and find an equation of the parabola. B. Find the depth of the satellite dish at the vertex. As usual, we're gonna draw the diagram based on the question first. The equation of parabola is y squared equals to 4ax. Y squared equals to 4 multiplied by 1.2x, and we get y squared equals to 4.8x. This is going to be our first equation. Let OD be the depth of the dish. Given width of the dish AB equals to 5 meter, AD equals to 2.5 meter. Let OD equals to x. The coordinate of A are OD, AD. Substitute the equation in first. We get 2.5 squared equals to 4.8x. X, we get 1.302. Required depth of the dish is 1.3 meter.
Next, I'll be presenting the last question. Given from the diagram, the water issuing from the end of a horizontal pipe 7.5 meter above the ground is called a parabolic path. The vertex of the parabolic path is at the end of the pipe A with the coordinate 0 and 7.5. We're going to find out how far beyond this vertical line will the water strike the ground. Given that the equation is x squared equals to negative 4a times minus 7.5. B is a point 2.5 meter below the pipe, at which the distance of the pipe of water flow is 3 meter. So we know that from A to B is 2.5 meter, and from B to C is 3 meter. First, we have to find out the length of O to B. So 7.5 minus 2.5 equals to 5. Hence, the coordinate of C is 3 and 5. Then we'll substitute it into the equation. 3 squared equals to negative 4a times 5 minus 7.5. And we'll get that 4a is equal to 9 over 2.5. To find the distance at which the water strikes the ground, we have to substitute the value of 4a and put y equals to 0 into the equation. Then we'll get the equation of x squared equals to negative 9 over 2.5 times 0 minus 7.5. And we'll get that x is equal to 3 times square root 3. So the answer will be the water strike the ground at a distance of 3 square root 3 beyond the vertical. In conclusion, conic section, particularly the parabola, are the fundamental mathematical concept that directly impacts our daily lives. These mathematical curves are essential in physics, engineering, and various other fields. Their practical applications are widespread and integral to our understanding of the physical world and technological advancement. Here are some of the references used by us to complete this assignment. That's all from our presentation. Thank you.